Okay, path of reaction, effect of a catalyst. Equilibrium constant describes how far a chemical reaction will go, but the reaction rate tells us how fast it's going to get there. A reaction will always get to equilibrium eventually, but some reactions will take a really, really long time and others will go very quickly. The activation energy is a barrier, an energy barrier that has to be overcome in order for the reactants to be converted into products. That's the minimum energy required when those reactants collide in order for the reaction to occur. They just bump into each other real gently, nothing happens. Most chemical reactions have activation energies because in most reactions you have bonds that have to at least begin breaking before you can form new ones. And there's got to be some energy provided for that. So we can look at the progress of a reaction by drawing a little diagram here. So we're showing energy increasing as we go up, and this is the reaction pathway, sort of similar to time. So we start with our reactants, and they have a certain amount of energy. In order for them to react, we have to get over this hump. We need to get enough energy to get over the hump, and once we get up there, it's all downhill and the reaction will proceed. That hump represents breaking the bonds that are in the original reactants. At a higher temperature, at a given temperature, the higher the activation energy, the slower the reaction. Because high activation energy means fewer reactant molecules can make it over the barrier, so you get a slower reaction. So I think of this as being a little bit like playing miniature golf. There's a miniature golf course in chemistry land, and so here's no, that's wrong. That's upside down. You gotta do it right. Okay, so there's a person playing miniature golf. And this is one of those humps in the miniature golf course, right? They've got all these bumps and stuff that you have to get over. And so you hit the ball, and you don't hit it hard enough, and it goes partway up, and then it rolls back. Dang, there's one stroke. And you try it again, and almost not quite. It won't go over the hump unless you hit it hard enough, you give it enough energy. If it has enough energy to get up to the top of the hump and just over the peak, then it'll be fine. It'll go down into the rest of the course. Does that make sense? There's got to be enough energy to get these reactants over this hump we call activation energy. Well, how can you speed up a slow reaction? Well, you can increase the concentrations of the reactants, because increasing the concentrations means there's more collisions. Are all of the collisions successful? No, but some of them are. And the more collisions you have, the more successful collisions you will have, and so your reaction rate will go higher. You can increase the temperature. When you increase the temperature, the particles, whether they're in a solid, liquid, or gas form, have more kinetic energy. They will collide with more energy, and more of the collisions will be successful. They'll have enough energy. There'll also be more collisions. Or you can use a catalyst. And a catalyst just lowers the activation energy barrier. So, illustration from your book. So here we're pushing rocks up and over this hill, so they'll go down here. I think the miniature golf analogy is a little more realistic. Anybody been pushing rocks up over a lump like that recently? I haven't. Anyway, you got to get them up over here, and it's going to take a while. That's going to be slow. You got to get them up. So the catalyst gives you an alternate pathway. So on the miniature golf course, there's this hump, but over to the side, there's no hump, or the hump is smaller. So if you hit it over in that direction, it doesn't need as much energy because the hump is less. The activation energy is less. So this hill analogy, we can increase the reaction rate by pushing harder. That's essentially increasing the temperature in a chemical reaction. Or we can find a path that goes around that hill, and that's using a catalyst. It gives you an alternate pathway. So here's our miniature gopher. The black is the original hill to get over. It requires a lot of energy to hit it up and over that hill. A catalyst will cut that hill down, reduce the amount of energy needed to get over. It may be an alternate pathway, or it may just cut down the energy needed in the original pathway. It's an alternate pathway. So the guy hitting the golf balls here, more of them are going to have enough energy to get over, and so the reaction rate's going to be faster. Enzymes are biological catalysts. There are probably 50 gazillion reactions occurring in your body right now, chemical reactions. Most of the reactants and products and other chemicals in your body are sensitive to temperature. If you heat the temperature up to increase the rate of reaction, you're going to destroy the molecules. So that's not going to work. And a lot of the reactions that occur quite slowly, and that's not consistent with life. So how do we speed up these reactions? Your body uses enzymes. Enzymes are catalysts. They can be used to increase the rate of a reaction without changing the temperature. You probably know that your body maintains a pretty consistent temperature. You may feel hot and get sweaty, but your internal temperature is still pretty close to 98.6 degrees Fahrenheit. That's normal. When things are haywire, when you're sick, it goes up. And that's your body's way of fighting off infections. But we can't just increase the rates of reaction by increasing temperature, and we can't really mess around with concentrations either. So enzymes are critical in how your body operates and controls the reactions that occur. So taking a molecule like sucrose. Sucrose is two sugars, glucose and fructose, that are bonded together. In the process of metabolizing sucrose, it needs to be broken into the two monosaccharides. Well, that requires an activation energy to break that bond. And the activation energy is high enough that this does not happen at a significant rate at body temperature. So does that mean you can't metabolize sucrose? Nope. You have an enzyme called sucrase. This lowers the energy needed and so speeds up the metabolism of sucrose. Think we've got it? Yeah, we've got a picture here. So here's a representation of sucrase, the enzyme. The enzyme has active sites, like little landing sites for the sucrose molecule. And when the sucrose molecule lands in here, stress is put on that bond. So it fits in really nice, but only if it stretches that bond. That makes that bond easier to break, and so the reaction will occur more rapidly at the same temperature and the same concentration. Any questions? Lots and lots of enzymes in your body, and they control things. They control whether a reaction happens at a significant rate or not.